So what does this boil down to? Well, the left-hand side here, you remember, before we can apply the map phi to this m plus n, we have to put these two together using, remember this was A star B, that's what this meant in this case, but we have to put these two together in the group G, which in this case is the clock group, integers modulo 12, before we can apply phi to them. Now, how do you put these together? Well, you remember, you take the equivalence class of m, the equivalence class of n. The way those add together is it's the equivalence class of m plus n. So it's essentially, the difference between these two is there's a bar over the individual letters here versus here there's a bar over the sum. Now, it's easy to get confused or messed around about what's really the significance of what's going on there. Well, so what this means here, m is just some integer, and then putting the bar over it means that you take that integer plus all multiples of 12, and every integer that's of that form, you collect those all in a set, and that whole set is this m bar. And then you do the same thing with n. You take whatever this integer n is, and you can add any multiple of 12 to it, and then you take all those. Well, what this is you're adding m plus n, and then you're adding a multiple of 12. So the reason why this is the same as this is because it doesn't matter whether you add a multiple of 12 to m, and then a multiple of 12 to n, and then add them together, or if you add these together first and then add a multiple of 12. Blah, blah, blah. You know, you can think about that more. But in any case, what the map phi does, I told you what it does. It takes whatever integer you have here under the bar, and it performs the rotation operation on that integer that many times. I mean, on the square, that many times as that integer. So what that would say, and I'm going to have to erase this just because I don't have room, but what that would say is that this whole thing here has to be the rotation operation performed m plus n times. That's what the left-hand side has to be. Now, similarly, the right-hand side, this one would be the rotation operation performed m times. This one would be the operation performed n times. So what this would say is that if I perform the operation n times and then perform it m more times, is that the same as if I perform it m plus n times? And obviously it is. And so you could say, oh, well, yeah, you know, this checks out. There's actually a subtlety here, which is very well worth pointing out. And this is that it's not obvious that the map itself is a well-defined map. See, this map here, taking n, the equivalence class of n over to r to the n. And the reason why is because here I've taken an equivalence class which consists of, you remember what it consists of, it's not only n, but it has n plus 12 in it, and it has n minus 12 in it, and it has all these other numbers in it. Now, for it to make any sense for me to say that I take this equivalence class and I send it to the operation where I rotate that square n times, it's not at all obvious that it would be the same if I took this particular n, or if I took the n plus 12, or if I took the n minus 12, or what, because this equivalence class has all of those in it, any, you know, n plus any multiple or minus any multiple of 12. So for this to work, for this to actually even be defined as a map, let alone be a homomorphism, it had better be the case that it doesn't make any difference if I add a multiple of 12. In other words, if I rotate an extra 12 times, it won't make any difference to what I get. So you see, the reason this works is essentially because 4, which is the number of times you have to rotate the square to get back to your starting point, 12 is a multiple of that. So if I rotate it 12 times, or 24 times, or minus 36 times, which would mean 36 times in the other direction, it's not going to make any difference. It's all going to come out to be the same. So this is a little tricky. In this case, provided that the map itself was well defined, it's automatic that it will turn out to be a homomorphism. This is sort of a laws of exponents thing. Now, you shouldn't necessarily take laws of exponents for granted when you're studying something like abstract algebra, because the whole point is to try to, understand these things at a deeper level. But if you remember what the symbols mean, it is clear that this is true, because what this symbol means is rotate the square clockwise n times. And then this one says, then, after that, rotate it m more times. Whereas this one says, rotate the square clockwise m plus n times. It obviously mean the same thing. But it only works if the original definition of the map itself makes sense. If this was a pentagon, for example, then it wouldn't work. Because what would happen is I could say, well, okay, suppose n, for instance, suppose n equals 7. Well, the equivalence class of 7 is the same as the equivalence class of 19, for instance, because I've just added 12 to it. If I take this and I perform on a pentagon, if I perform r to the 7th, that certainly is not the same as if I performed r to the 19th, because it differs by a multiple of 12. And if I rotate the pentagon around 12 times, and in this case I wouldn't be rotating by 90 degrees, but if I rotate it 12 times, it'd be, if I rotated it 10 times, then it would come back to where it was, and then 2 more times it would come back to something different. So anyway, you can rewind this and try. You can even play around with it. Mess around with a pentagon and convince yourself that this definition wouldn't make any sense if I have z mod 12z here. Now, if I had z mod 15z, then it would work. Why? Think about that. Why? It would work for a pentagon, that is. And if z mod 15z would not work for a square, why? Once again, think about that. Why? But anyway, this gives you a very concrete example of what a group homomorphism is. And I think it also gives you an idea of why one would be interested in such a thing. Because it's something that allows you to relate two different structures in a natural way. It's something that allows you to see what part of this structure is actually reflected in this structure, and to some extent vice versa. So in later videos, we need to go on and talk about different kinds of homomorphisms, do some more examples. In particular, we need to talk about the idea of isomorphism, which is a homomorphism that preserves all the structure and that actually gives an equivalence of structures in a group theoretic sense. But that we will do in a later video.